Hello and welcome. For years, the exciting news was simply finding planets outside our solar system, exoplanets. But we've entered a new, perhaps even more thrilling era, the age of exoplanet characterization. We're no longer just counting planets. We're trying to figure out what they're actually like. So, what does characterization mean? Well, finding a planet using methods like the transit method, watching for dips in starlight, or the radial velocity method, seeing a star wobble, tells us things like how long it takes to orbit its star, its distance, maybe its size or minimum mass. Characterization goes much deeper. We want to know, does it have an atmosphere? What's it made of? Are there clouds? What's the temperature? Is it rocky, gassy, or icy? Could it potentially support liquid water? Getting these details isn't easy. We're dealing with faint signals from incredibly distant objects, often drowned out by their host star's glare. But astronomers have developed some ingenious techniques. One key method is transmission spectroscopy. Imagine a planet passing in front of its star. If it has an atmosphere, some starlight filters through it. Different gases in that atmosphere absorb specific colors of light. By analyzing the starlight during the transit compared to asterisk before or after sounds, we can identify the atmospheric ingredients. Think of how Earth's atmosphere changes the color of sunlight at sunset. It's a similar principle, just much subtler. The James Webb Space Telescope, or JWST, is incredibly powerful for this. Then there's emission spectroscopy. Here, we measure the light coming from the planet itself, its heat glow or reflected light. Often, this is done by observing just before a planet disappears behind its star, and then comparing that combined light to the light of the star alone when the planet is hidden. The difference tells us about the planet's own radiation, revealing temperature and more atmospheric composition details, especially for hot gas giants. Direct imaging is exactly what it sounds like, trying to take an actual picture of the planet, separate from its star. This is extremely difficult because stars are so bright and planets so faint and far away. It needs sophisticated technology to block the starlight, but when successful, it gives us direct confirmation and allows us to study the planet's light directly. Another clever technique involves observing phase curves. Just like our moon goes through phases, an exoplanet shows different amounts of its illuminated or heated side to us as it orbits. By carefully measuring the total light from the system over time, we can detect these subtle changes, which can reveal how heat is distributed, suggesting winds or stark day-night temperature differences. And don't forget density. By combining the size of a planet from transits with its mass, often from radial velocity, we can calculate its overall density. This is a fundamental first step, telling us if we're likely looking at a puffy gas planet like Jupiter, a dense rocky world like Earth, or something in between. What have we learned so far? Incredible diversity. We've found planets with atmospheres ranging from clear to hazy, containing water, methane, carbon dioxide, and more. We've seen extreme climates, worlds tidally locked with permanent scorching day sides and freezing night sides, planets hot enough to vaporize rock. Clouds seem to be common. We're confirming the existence of many rocky worlds alongside the gas giants. Of course, there are huge challenges, especially when studying small, potentially Earth-like planets. The signals are tiny, but telescopes like JWST are already making huge leaps. And looking ahead, giant ground-based telescopes and future space missions promise even more exciting discoveries. We're moving beyond just taking a census of planets to actually diagnosing their nature. It's a journey that's fundamentally changing our view of the cosmos and our place within it. Thanks for listening.